Yes, thanks for the opportunity to give this presentation. What I've heard in the two presentations this morning already is a lot about opportunity, about collaboration, and about partnerships. What I will do in my presentation is to talk about the same aspects, but do it from a technology development point of view. And I'll try to answer what step change will be all about. So if we look at technology development from a BASF point of view, there are always a couple of different disciplines involved. First of all, if we would have developed a new process technology at BASF a couple years ago, we would have done it in a way that we have developed a certain process together with the catalyst, and would have done it having the idea in mind to use that technology in-house. And you see, this is all a lot internal focus. What we've tried to do over the last years is to move away from that internal focus, to open up and to more go towards partnerships and open collaboration in a way that BASF is not taking all of those three roles anymore, but that we are doing it in a collaborative way where we would just take one or two of these roles and partners are taking other ones. From our point of view, it's time for partnerships, and the world is getting just too complex to do all of these different tasks in-house. And I'll show you in a couple examples how we are doing that, how we are unlocking additional value through cooperation, and how we do that in the area of technology development. So first of all, let's have a look on how a joint development project in the area of process technology looks like. What we will hear a lot about today and tomorrow is starting on the right-hand side of my chart, where a certain commercial technology is available. What I will focus on in my presentation will be more the parts on the left, where you are starting with an idea at a certain point in time and think about how we can develop that idea through the different phases of an innovation process until we are at a point where a new technology is commercially proven and can be operated in a commercial plant. Now, unfortunately, there are a lot of steps in between, and I mean, one approach in this whole innovation project is to do all these steps as an internal project. That's the one I've described on the previous slide, and we are not doing that too much anymore. What we try on the opposite is to bring partners in, not just here at a late stage where it's about proving and demonstrating a technology and commercially using it. What we try to do is to partner with external companies already here in the very beginning and develop technology development opportunities together with partners from the very beginning in this process. So what could that mean from a BASF catalyst point of view? Well, a very typical setup for what my team is doing is to work together with engineering partners in a way that we do collaborative projects, typically in a joint development framework, where BASF is focusing on catalyst development, where our partners in most of the cases are focusing on process development. And by doing these projects in a joint way, we end up not with a process and a catalyst as two separate items, but we end up with a package of those two where the full synergies of those two aspects are leveraged. How are we approaching ideation? Well, again, we are approaching ideation in a very collaborative way. We are starting here in the very beginning to talk to partners in a very early stage. In the extreme case, in a stage where we don't have data on a certain technology on the table, but just at a stage where we only have an idea or a concept, and where this idea is matching a certain need or a demand a partner has in a certain value chain. And actually this type of conversation we are having here today and tomorrow is a very good starting point for this type of technology development, because we talk about needs you might have in certain value chains, areas for improvement of technologies, and whenever you have those topics, in cases where it's related to a catalytic process, I'm more than happy to discuss those with you a bit further. A question I often get if you look on such joint development projects is, how do you manage IP? And IP always is a critical point when it comes to developments. However, I don't have a black and white answer how we handle IP. And I'll show you in a moment how different options could look like, how to do it. So what you see here is a very typical setup how we are working in partnerships together with partners. What we typically do is a setup where BASF is covering catalyst development. This was too quick. Where we are doing catalyst development, so developing catalysts from a very early stage, but also doing testing of catalysts and development on larger scale, where in parallel our partners, typically technology providers or engineering companies, are doing process design, are doing optimization of processes, are doing demonstration of those technologies on larger scale. And I have one example here where we are working together with Linde Engineering on a dry reforming technology, which will be one of the case studies I will talk about in a moment. So now, those are the two individual tasks and the roles and responsibilities of the two partners. And whenever it comes to business topics, whenever it comes to generating value with the combination of that new catalyst and new process, we are typically doing that in a joint way. Specifically when it comes to launching and marketing of a new technology, typically that is done in very close collaboration with our development partners. So let's move on and show you in two case studies what such a partnership model is all about. What you see here is various value chains, how you can make olefins. Olefins being one of the key intermediates in chemical industry. And as you can see here, there are a lot of different routes to make olefins, either starting from naphtha, starting from alkanes, starting from methane in the more recent times. And on the right-hand side, you see an additional range of technologies where from different raw materials you go through syngas as an intermediate and then convert that syngas typically in multi-step processes into the targeted olefins. Now the question I got when I looked at these value chains a couple years ago was, aren't these all very mature value chains, and is there really room for differentiation and room to develop new technology in this very crowded space? Actually, the answer I can give in the meantime is that there is a lot of space left, there is a lot of opportunity, even if you look at these very mature value chains. What I would like to show you as two case studies is one example where we look here in the conversion of natural gas into syngas, so the early step in this process chain. And I will show you a second example, which is about converting that syngas that has been made in the first step through dimethyl ether, which is basically a methanol equivalent, and a very good starting point for conversion of that intermediate into downstream olefins. So first case study will be on natural gas conversion to syngas, while the second case study will be about converting that syngas into a methanol building block. Okay, so no animation on this slide. Let's try to do it in this way. The case study here is about a technology we are developing together with Linde Engineering in the space of steam methane reforming. And if you first look on how steam methane reforming looks like, you're basically talking about a conversion of natural gas with an excess of steam in a temperature range above 900 degrees C typically, where you then make your target molecule syngas. If you look at it from a product ratio point of view, you can see that typically you end up in a certain range of hydrogen to CO ratios. And now the question we asked ourselves is it also possible to move from this range of product distribution more towards the lower ranges here, which are typically not accessible by steam methane reform. What you typically do if you would like to move in that direction is that you apply technologies like partial oxidation or autothermal reforming, where you have the need for pure oxygen. And that pure oxygen always comes with the need for an investment in an air separation unit, which is a pretty costly step. So what we try to do in our project is to develop a new technology where we can do methane conversion under drier conditions. That's why we use the term dry reforming. Do it in a way that there is no need for oxygen in the process, and do it in a way that we can assess hydrogen to CO ratios below 2, so exactly in that range where you typically cannot go with conventional steam reforming technologies. So the technology I'm presenting here is one where the targeted downstream applications are CO or are high CO syngas applications, and we talk about basically extending the hydrogen to CO range that is accessible with steam methane reforming. Another nice feature of the technology is that you cannot just do it under drier conditions and thereby reduce steam consumption, but you can do it in a way that you can also chemically utilize CO2, and in the extreme case convert methane and CO2 under very dry conditions without the use of oxygen into a very high CO-rich syngas, and do it in a way that you do it at comparably low OPEX, and in a way that if you build a new unit, you can do it in a very capex efficient way, so at lower capex compared to conventional technologies. So let's have a quick look on how such a catalyst looks like. You know, I'm a catalyst person. That's why at least I want to show you two pictures. What you can see here on the top is one catalyst for that technology that can already be operated under comparably dry conditions. This is a catalyst that is typically a good solution for a drop-in into an existing unit, or for a revamp of a steam reforming unit where you want to go to a moderately decreased steam to carbon ratio. And this is actually a technology we are not just talking about in an early stage. It's a technology where we are in early launch phase in the meantime, and it's one of those examples where we've applied that partnership model, or where we started to do that partnership model already several years ago, and where we are now in a later phase of the development. There's a second catalyst you can see here. For the chemists in the room, this is a cobalt-based catalyst. That's why it has the nice color. This is now a catalyst where you can go towards steam reforming under even drier conditions. And this is now really an example for what I call a step change technology. Step change here being that you can do reforming of natural gas in the presence of a very high concentration of CO2, and can do it in a very cost-efficient way. For this catalyst and the related process technology, we are currently in pilot phase. so a bit behind the first generation of the technology, and we are now progressing that in parallel to launching the first generation product. So this was one case study, and let's now think about, in a second case study, assuming we have made syngas in an efficient way, what can we do downstream? How can we chemically utilize the syngas? The example I've chosen here is another of those collaborations we do together with partners. As this is the next downstream step of the first technology, this is another project where we are working together with Linde Engineering. And in this case, it's about looking at a value chain where you convert syngas typically in a two-step process through methanol as intermediate into dimethyl ether, which then subsequently could be converted into olefins, for example. So the conventional technology is a two-step technology with all its limitations on the thermodynamic side, while the new process we are developing together with Linde Engineering is a more efficient one, where those last two steps are combined in one reaction step, and where we take advantage of the favorable thermodynamics of the syngas direct conversion to DME. To be more specific, if you look at a certain temperature, you can almost achieve full conversion if you do it as a one-step reaction, while you are very strongly conversion limited if you do it through a two-step process. Also for this technology, we've developed a tailor-made catalyst that can do that job in a one-step process, while in parallel our partner has developed a process concept. And again, we've done it in a way that both of those aspects come together in a synergistic way, allowing the overall new process concept to be a very efficient one. So what was the technical hurdle here? For this specific case, the technical hurdle was that a lot of catalysts can do that job, but that those catalysts suffer from a very significant catalyst deactivation. And without going in the details of the development here, what we've achieved and the technical hurdle we've taken is that we came up with a catalyst formulation that is much more stable, and only that stability of the catalyst is allowing that process technology to make economic sense and to be economically viable in the end. What you can see here is how we are doing that development in terms of testing catalyst and in terms of developing the process. So here the hidden picture is showing testing of catalysts on very small scale in a high throughput mode. And you can see there are various test configurations in between. Currently we are here on mini plant scale, where we are looking at about 1 kilogram of catalyst and the related concentration of DME. And the next step we are now working on is to demonstrate the performance of the technology we've seen on that scale on the next larger scale, which would be the operation of a mini plant in this case. Why do we now think this new process technology is a more efficient one? Well, just to give you two aspects of the technology, and again you can see here the comparison between a two-step route and a one-step route. If you look at energy efficiency, and it's described here as cold gas efficiency, our new process is up to 10% more energy efficient. And if you look on emissions, emissions of CO2, for example, the two-step technology is forming about 30% more CO2 emissions versus the new technology we are proposing. And if you look on the emission side, there are other advantages of the direct technology. for example, like the formation of significantly less wastewater in the process. So again, what we are doing is to take advantage of favorable thermodynamics of a one-step route versus a two-step route. We are doing that in a setup where the syngas generation can be done in the way I've described in the first process, in the first case study, but where also syngas coming from any different source can be done, and where the overall high energy efficiency is achieved by implementing heat recovery and energy integration in a smart way. So if you look on that from a cost of production point of view and compare again the direct DME route with the two-step process, you can see that there is a significant advantage in terms of efficiency and in terms of production cost with the new technology. And the step change we are looking at is basically here the delta between those two bars. And if you look in more detail where that delta is coming from, in this specific case, it's related to the fact that the same amount of syngas can be converted into more DME with our technology versus the two-step route. And the other aspect is that on the utility side, for example, regarding steam, the two-step process is something where you have to import steam, while in our case the reaction is done at a different temperature level, allowing the overall process to export steam, and that's another reason why the one-step route is a more efficient version. So what we are doing in the next step is to take that technology we've developed on lab scale and proven on mini plant scale, and we are now working together with several partners who have interest to take this technology into the next scale and prove it on piloting scale. And in this specific case, we are doing it in a way that not BASF or our engineering partner is operating that pilot, but in this case we are looking at building the pilot together with an external partner and operating that pilot hopefully over the next 1 or 2 years. So here one opportunity to partner is on piloting this type of new technologies. A second opportunity obviously is in the next step, once the technology is proven on pilot scale, to adapt such a step change technology at an early point of view once it's proven on pilot scale. I've shown you 2 case studies that were about developing step change technologies, and they have not been chosen by coincidence. They have been chosen based on the fact that my team is not focusing on doing incremental improvements of technologies. We are really looking for those rare opportunities where you can make a larger step in terms of improving technologies. And you've seen 2 examples of what this could be all about. In terms of our scope and the value chains we are interested in, certainly we are looking into those value chains that are relevant for BASF from a producer point of view, but we are also looking beyond that, and we've made the conscious decision to not just do those developments in area where the company itself would use the technology, but we also do it in cases outside that, driving technology as well as catalyst business for BASF. And obviously, all of that is building on partnerships, and on our side, it's of course building on the capabilities on the technical side that BASF can bring to the table. So summarizing what you've seen, there are a lot of different options how partnering and how collaboration is possible. From a BASF Catalyst point of view, we are of course interested to sell products in our current portfolio, but we go beyond that. There are examples like the one you've seen in the video in the beginning, where we are making BASF process technologies available to third parties. And I've shown you a couple examples where we are going beyond that and starting in technology development very early in terms of doing partnerships and collaborative projects. So there's basically a broad range of different options how to work with BASF when it comes to technology developments. So what we are looking for is technology developers, technology providers, engineering companies, users of technologies who are interested to develop step change technologies. We are always open to have an open exchange about ideas, about concepts, about new projects in that space. Our role typically in this type of project is that we contribute on the catalyst side, while in many of the projects our partners would contribute on the process side. And by bringing those two pieces together, we have a very good basis to develop step change technologies and to come up with technologies that at this point in time we can just see in our crystal ball. Thanks very much.